So, differentiability, we're going to talk about two different types of differentiability. We're going to talk about being differentiable at a point and differentiable over an interval. So the first blank here is going to be differentiability at a point. So a function is differentiable at x when its derivative exists at x. Okay, so if you can find the derivative at x, then it is differentiable at that point. Differentiability on an interval is pretty self-explanatory. A function is differentiable on an open interval a to b when it's differentiable at every point on that interval. Okay. Continuity, we had a similar definition. Our function was continuous as long as it was continuous at every point on that interval, right? So similar to continuity, differentiability, we're going to be looking for places where something is not differentiable. Okay? So, all right, consider the function f of x equals absolute value of x plus 3. I want you to find these three things for me. Oh, sorry, I didn't scroll down. Okay, oh yeah, this one's really important. I didn't scroll down. A function must be continuous in order to be differentiable. If you have a hole or a jump or an asymptote on the graph, it is not differentiable, right? So, because it is not continuous. So, everything we've learned about continuity has to be taken into consideration, and then we're going to throw differentiability on top of that. All right, so this is like the warm-up. Go ahead and fill this in here. All right, so Reagan, what is f prime of negative 5 for this graph? It's negative 1, perfect. Bo, what is f prime of 0 for this graph? It is 1. Okay. Troy, what is f prime of negative 3? It's not. It is a minimum point there. But in order for it, like you could draw a tangent line, I agree with that. But because this is not a smooth curve, it is not differentiable at that point, okay? So this would be, so 0 is not a bad guess, because if that was curved a little bit, it would be 0, because you're looking at that minimum point. And technically, I guess it is a tangent line right there, but we're going to look at limit definition of a derivative for this a little bit more. And as I approach from the left, what's the slope as I approach that point from the left? It's negative 1, right? And from the right, the slope is positive 1. And it's not a gradual change to become 0 right there. It's just a sharp turn in the graph. So this would be, I should have looked up yesterday whether to call this undefined or does not exist. I'm going to go with does not exist. I could, but you guys need some time to work on your work in class, so I'm not going to. I'll look it up later. All right, so there's a chance that's supposed to be undefined. I got to look at it. But definitely there is no derivative at that point for that one. I need to zoom out a little bit, don't I? There we go. All right. Functions are not differentiable at sharp turns. You can have, if it is a smooth turn, if it's curved, if that was like a little bit curvier and looked like that, then it could be differentiable. But if you have a sharp turn, right, so any type of sharp turn where it's a little bit pointy, your function is not differentiable at that point. A word that is sometimes used for this is a cusp. If you have a cusp, you're not differentiable at that point. Or you can just call it a sharp turn. It's fine to call it a sharp turn. Sharp turn on the exam's fine. You could use cusp if you want. A few years ago, several of my students liked to say that word cusp. They thought it was funny. So you can use it if you want. Yeah. There is a chance that it could be used within a problem. That's why I want to throw it out there. But as far as writing your answers, you can use it if you want, but you could also just call it a sharp turn. All right. In order for a function to be differentiable at a point, first of all, f of x must be continuous. I guess I should put continuous at x equals a. So for us to have differentiability at a point, the function has to be continuous at that point. Okay, now it could have a discontinuity somewhere else, but at that point it must be continuous. If it's not continuous, it's definitely not differentiable. Now, something can be continuous and still not be differentiable, but if it's not continuous, it's definitely not differentiable. The other thing that we have to have happen is the derivative from the left has to equal the derivative from the right. But we don't really have notation to say derivative from the left equals derivative from the right. I'm going to write it out in words here. So derivative, you can, yeah, of f of x from the left equals derivative of f of x from the right. Now, we can't really write this out. There's not really notation for that. We can't really do this without using limit notation here, because limit notation is how we show that something is coming from the left side or the right side. So what we need is we need the limit as x approaches a from the left of, we're going to use that limit definition of a derivative at a point that you may have already blocked out of your mind. It was f of x minus f of a over x minus a. It must equal the limit as x approaches a from the right of f of x minus f of a over x minus a. Okay, and we'll go through how to do this here in a second. A function is not differentiable at points of discontinuity, so holes, asymptotes, jumps in the graph. If you have any of those, you're definitely not differentiable because you're not continuous. At sharp turns in the graph or at vertical tangents. Vertical tangents are a little harder to see. It's when, let's see, if I had like x equals y to the third, this is an example of something that would have a vertical tangent line. Let me see if I can do this one. Y equals, well, let's do y equals, or f of x. Let me see if I can get this to show. equals cube root, let's just do x to the 1/3. Alright, and then y equals f prime of x times x minus a plus f of a. Add a slider to see if this happens. Oh, f prime of a. There we go. There's our tangent line. No, yeah, it's a kind of a weird tangent line, but if I look at this, it's a tangent line at this point, but it does run into the other part of the graph here. So at this point, it is tangent to the graph because it's just touching at that one single point. It could be considered a secant line when you're looking at it this way. If you are looking at this point, the point where it kind of just bounces off of the graph, you would call it a tangent line. If you are using it to estimate like something in between here, then it would be you would call that a secant for that. This happens sometimes when you have sort of weird shaped graphs. Your tangent at that point may run into the graph somewhere else. I probably should be more precise in my definition of tangent line, because this is a tangent line even though it does hit more than once. Yeah. So if we're over here, you can see this tangent line right here is getting steeper and steeper and steeper, and I can't quite get there because if I go to 0, it goes away. But if I do, let's see if it'll let me type in. Like if I do 0.01 and then do 0.001 and 0.001, you can see how that almost becomes vertical. Technically it's not, because if I go to 0 it disappears, but this is an example of a vertical tangent line that you would have here. And what is the slope of a vertical tangent line? Undefined. It's undefined, so that's why we can't be differentiable at that point, because if you do take the derivative, it's undefined, because the slope of the tangent at that point is undefined. So here's an example. We want to know, is f of x differentiable for all values of x? These problems take a little while, because what do we have to prove before we can prove differentiability? Continuity. If it's not continuous, it's not differentiable. There are some instances where if you just go straight to looking at differentiability, it's going to look like it's differentiable, but it's not, because it's not continuous at that point. So you always want to check continuity first. So there are 3 things we have to prove for continuity. We got to show that the limit as x approaches a of f of x exists. We got to show that f of a exists. And we've got to show that limit as x approaches a of f of x equals f of a. For this particular problem, since it is a piecewise function, to show the limit exists, we've got to do the limit from the left and the limit from the right. So we would do limit as x approaches 0 of f of x, which, 0 from the left. From the left, we would use that top function, so that would be the limit as x approaches 0 from the left of x plus 1, which would just be 0 plus 1, which is 1. From the right, we will be doing the limit as x approaches 0 from the right of f of x, which is limit as x approaches 0 from the right of the bottom function, x plus 1 squared, which is just going to be 0 plus 1 squared, which also gives us 1. So since the limit from the left and the limit from the right both equal 1, we could say that the limit as x approaches 0 of f of x equals 1. One thing that a lot of you guys were doing on the test, you were stopping here when you were doing continuity, right? This is not enough. This proves that the limit exists. It does not prove we're continuous, because at this point we've just shown the limit from the left and the limit from the right equal each other, but for all we know there could be a hole in the graph at that point. So what we have to do is we have to find f of 0, which is normally very simple. In this particular case, you're just plugging 0 into that top, and you'll get 1 as well. And so we would say since limit as x approaches 0 of f of x equals f of 0, f is continuous at x equals 0. Now, that is only continuity. We now are going to have to prove differentiability. What they'll do for these a lot of times is they might, if it's a free response, part A will ask you to prove it's continuous. Part B will ask about differentiability. So we're kind of doing two parts in one here. So for B, for the second part, for differentiability, we are looking at, we got to say that it's continuous, which we just did, so check mark on that. And then we've got to do the derivative from left and right. And for this case, we are going to have to do the limit definition of a derivative. So that limit definition of a derivative at a point, so f prime of a is the limit as x approaches a of f of x minus f of a all over x minus a. Now, we don't have to write that down. I'm just writing it to make sure we remember what that limit definition of a derivative is. If we want it to be from one side, we'll do it from the left or from the right. So for this problem, we got limit as, well, let's call it, well, limit as x approaches a from the left. And so that is going to be f of x minus f of, oh, not, I should not use the a. What's the value we're checking here? 0. So we got 0 right here. And so we would be doing f of x minus f of 0 over x minus 0. And since we are doing this from the left side, f of x would be the top function. It's going to be x plus 1. We just found f of 0 from that side. It was 1. So f of x plus 1 minus 1 over x minus 0 is just x. So this ends up being x over x. What is x divided by x? Oh, I'm being so lazy. What have I done? Yeah, I've dropped my limit notation, and can I drop it yet? No, I have not plugged anything in. So I should be keeping my limit notation throughout. So x over x is just 1. The x's cancel. I'm just going to get 1 for this. Okay, now that's the left side. We've got to do the right side, so we got to do the limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0. For this, we're using the bottom function, so x plus 1 squared. F of 0 is still 1 over x. Now this one's a little more complicated than the last one. We're going to need to distribute here. So x approaches 0 from the right. We'll get square, double square, x squared plus 2x plus 1 minus 1 over x. And then these 1's cancel each other out here. So is it all right with you guys if I go ahead and factor x out of that numerator? That greatest common factor, so I'll have x times x plus 2 in the top. I'll have an x in the bottom. My x's will cancel. I will get 0 plus 2, which gives me 2. Is this function differentiable? It is not. Since limit, well, let's see. I don't want to word that. Yeah, I think I'm going to just do it this way. Limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0 does not equal limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0. F is not differentiable at x equals 0. So much work. Let's just zoom out to admire our work here. Lots. We don't need to not have that much room. No, you don't. I should make this. I should print this bigger on this one, shouldn't I? Yeah. Now, this is something you would see on a free response. Usually, they will break that into parts, where they ask for continuity in one part and differentiability in the second part, because it's a lot of work in one. Well, definitely not at South Stokes.
I think it's an easy drive.
All right.
I mean, it's definitely pretty curvy. You go what, 52? I don't know what 52 is.
All right. Here's an example of a multiple choice question that you might have. Let f be the function defined above. Which of the following statements is true? So all of your options are that f is not differentiable. But we need to know why. So this one is multiple choice. So you don't have to be quite as precise as far as checking for continuity. Now, if you are being precise, you would do the limit as x approaches 5 from the left of f of x. And that would be plugging 5 into the top function, which would just give you 2. And then you would do limit as x approaches 5 from the right of f of x, which would be the limit as x approaches 5 from the right of 2x minus 4, which is 2 times 5 minus 4, which is going to give you 10 minus 4, which is 6. So, what has happened here? It's not continuous. So we don't need to go any further. We don't need to check differentiability or anything like that. As soon as we see it's not continuous, then we know it's not differentiable because of that. Yeah, so A would be your answer for that. And really you can see this, since it's multiple choice and you don't have to show your work, you can just plug in 5 into both of these and see if you get the same number. That's checking continuity. If it was free response, show your limit notation for it. Okay, questions? All right, let's look at another one. Which of the following statements, if true, cannot be used to conclude that f of 0 exists? So, are there any here that you want to throw out? It cannot be used to conclude that f of 0 exists. What does it mean if I have a y, the graph of f has a y-intercept? I'm thinking about my graph.
It goes through the y.
It hits the y-axis somewhere, right? What's the x-coordinate there? 0, right? So this is some point 0, f of 0. So if I have a y-intercept, then f of 0 has to exist, right? Because I've crossed the y-axis there. So this could be used to prove that f of 0 exists. It's not really a calculus idea, but it could be used. Okay? Because to be continuous, what's part of proving something continuous? F of 0 has to exist, right? The limit has to exist, f of 0 has to exist. So we could cross out b, and since we crossed out b, can something be differentiable without being continuous? It cannot. So C is out as well. That leaves us A, so we're hoping that is the answer. And if you think, I really should mark that out. It looks like I colored those in. Not those, right? For limit as x approaches 0 of f of x exists, can you have a limit exist that looks like this that has a hole?
Oh,
Yes.
Yeah.
Limit is what you're approaching, not the actual value that is filled in for that point. So this is possible, so we cannot use A to conclude that f of 0 exists. Yes. Yeah. They love to give you problems like this where you've got to know several things from several different pieces there. All right. Okay. We have a free response question that we are going to practice here. And I realize I don't have enough room here either, and it's too tiny. So I might need to rethink what I put in there. Let's see. We'll get it as large as I can here. Let me rewrite your equation over here larger so you can. So f of t is 48t plus t squared minus t squared over 12. And then we've got g of t here. This is for 0 to 6. 0 less than or equal to t less than or equal to 6. And this is for 6. Oh, that's just a less than or equal to t less than or equal to 12. Okay, so according to the model, F, or this is, well, let's read the whole thing. At an excavation site, the amount of dirt that has been removed in cubic meters is modeled by the function f defined above, where g is a differentiable function and t is measured in hours. Values of g of t at selected values of t are given in the table above. According to the model f, what is the average rate of change of the amount of dirt removed over the time interval 6 to 12? Now, it's asking average rate of change. What are we going to do when it's asking us for average rate of change? Slope through the endpoints wherever our interval is, right? So we're looking at 6 to 12. From 6 to 12, we're supposed to use g of t, which we only have a table for. But slope through the endpoints we can do with a table, right? So we would have the point 6,306, and we would have the point 12,474, and we would do slope formula, 474 minus 306 over 12 minus 6. Now, on a for real test, you can leave it there. You don't have to go any further. I don't think this one is... Was this one calculator active? I really can't remember. Let me see what it is. We're going to make it calculator active for this, so... It's not like it's that difficult, but 6. Yeah, 168 over 6, and you'll get 28. Now, this one did not ask specifically for units, but we need to put units with this. So, what are the units for this?
Cubic meters.
Cubic meters per hour. Because we're doing a slope right here, right? Our y's up here, the top, this is cubic meters. And the bottom is hours, right? Because that's our x's on the bottom. So it's going to be cubic meters per hour. So dirt's being removed at a rate of 28 cubic meters, or an average rate of 28 cubic meters per hour. Yes?
You also write like m to the third divided by HR.
Yes, that'll be fine. The only thing I would caution on writing m to the third divided by HR, make sure you're very confident about where that exponent goes whenever you do the m to the third. Because sometimes people will put that 3 over here with the hours, and then that makes it terribly wrong. So just make sure you're very confident about it. Yeah, and it really would not, like, cubing an hour really doesn't make sense in the terms of context, right? So just be careful with that. All right. Okay, B asks us to use the data in the table to approximate f prime of 9, the instantaneous rate of change of the amount of dirt moved in cubic meters per hour. At time t, hours show the computations that lead to your answer. So we are estimating f prime of 9. What would we do with that?
You could take the 8 and the 10, those coordinates, and then estimate.
We're going to find the slope again. We're going to use the points closest to 9 this time because we're trying to get as close to the rate of change at 9 as we can. So we would have 428 minus 376 over 10 minus 8. So 428 minus 376 divided by 2 is going to give us 26. And this would be cubic meters per hour also. It tells you cubic meters per hour on that problem. If they put units in the problem, put units in your answer. Sometimes there's a point for that. Everybody okay here? No. I wish they would let us see them, but no. The only year they ever did that was COVID year. And COVID year, they did let me see everybody's responses. But the COVID year, they had a 45-minute exam that they took at home. I had 2 kids not even take it. It was 45 minutes, and you did it at home. And they didn't even bother to log in and try. It was open note. You could use anything. Because they can't give you something that's not open note if you're taking it at your house.
So, like, you could use, like, Desmos.
Yeah.
And they didn't even do it.
They didn't even try.
45 minutes.
45 minutes. They were not wasting 45 minutes of their life.
I would do that for sure.
Now, they were very smart about how they made the test where things like photo math or, like, it might help you to have your notes out, but you only have 45 minutes, so it's not, by the time you look it up, you're not going to get as much done. It was not a great test, but they didn't know that Luke McComb and Troy Snow were not sitting right next to each other helping each other on it. And they didn't know that Valeria didn't just, like, call in or that, let's use that example, that Jeremy just didn't call in his brother Jack to take it for him. Yeah.
Literally the whole class.
So,
the whole class
yeah.
together, like each person do like 2 or 3 questions.
Well, I think they did give every person different questions. There were a lot of different forms that year. But, well, not every person had different questions. But there were like 7 or 8 forms, or maybe even more, so it was unlikely that if you had 2 people that were together, they also had like they might have been able to tell if you were taking it together and like look at those because they had like cyber things watching you. Yeah. Everybody had to take it at the same time. It wasn't like a login whenever you want sort of thing. So, yeah. But you could easily have somebody in the room like that knew how to do it that was helping you, and they would never know. But I was glad that they did something that year because otherwise none of those kids would have gotten any credit, even though we were already like 3/4 of the way through the class whenever we had to go out for COVID. So, yeah, they weren't feeling it. Low motivation. Whenever I tell you guys that no one has ever failed calculus, that is because the year that COVID year, we technically couldn't fail anybody. But somebody would have failed calculus that year had I been allowed to fail somebody that year. He just didn't get credit. It didn't go on his transcript as an F. He had about a 15 whenever we went out for COVID. And could have brought his grade back up had he done any of the work that I assigned. But did not, and then did not take, I mean, honestly, maybe it was a waste of his 45 minutes to take that exam. But now the other one I don't know. I'm not sure why she did not. And, I couldn't really, make her because I wasn't there. So, anyway. Yeah. All right. So, it was a lot of questions. They put so many questions on there, they really didn't expect you to answer all of them. It was a weird test that year. Weird test. They, I'm sure, never want to do that again. And hopefully we will never have to do that again. All right, so continuity. Continuity, we need the limit from the left and the limit from the right. And we're proving continuity for this entire function from 0 to 12. Not at a single point, but from 0 to 12. So we have to tell why f is continuous from 0 to 6, why it is continuous from 6 to 12, and then we've got to check that point at 12. Right? So, is f going to be continuous from 0 to 6? Okay? It is because it's got a cube right there. It's just a cubic function, or you could call it a polynomial function. It does have a fraction, but does that fraction have any possibility of making this undefined? No, because you just have, this is really like having 1/12 times t to the third. You don't have a variable in the bottom of the fraction. So we would say for this, since f is a polynomial or cubic function for 0 less than or equal to t less than 6, f is continuous on this interval. I think in the equation it's a less than right there, so we want to use a less than. Okay. Then we have to look at why g would be continuous. All we have for g is a table. That does not guarantee continuity at all, because we've just got a few points. We have no idea what's happening in between. But there is something they tell us about G that guarantees it has to be continuous. It tells you G is a differentiable function. If G is differentiable, it must be continuous. Since G is differentiable, G is continuous. Are we proving that G is continuous? We're proving F, right? It's asking us about F. Therefore, F is continuous. I believe right here we need to do 6 less than t less than or equal to 12. I don't think we need to put the or equal to sign right there, because 6 we still got to test continuity for that. I should say 4. Okay, so we've proven everything but the point at 6. So now we need to do the limit as x approaches 6 from the left of f of x, which will be if we plug in 6 into that equation. So 48 times 6, what was it? Plus 6 squared minus 6 cubed over 12. We're going to use our calculator for that. I can't remember if this was calculator active or not, but we don't have time for all of that. All right, I'm getting 342. Is that right? It's not going to be continuous if it's 342. Let me use some 80 for this one. Let me make sure I've done that right. Did you guys get 342? Somebody else tried it? No, I got 306. I think I typed it in wrong the first time. That's better because you can't really do D if it's not 306. Okay, our limit as x approaches 6 from the right of f of x would really just be the limit as x approaches 6 from the right of g of x, because for 6 we're using the function to the right. And what is g of 6? It is 306 from that table, so it equals 306. We also need to show that f of 6 equals 306, which it does. You can just write that down, it's fine. So we'll say since the limit as x approaches 6 of f of x equals f of 6, f is continuous at x equals 6, and thus continuous on the interval from 0 to 12. It is. All right. D asks us for the instantaneous rate of change in the amount of dirt removed in cubic meters per hour at time t equals 2. So we need the derivative at 2. At 2, which function are we using? Top one or bottom one? Top. It asks for 2, so do we really have to do a left and a right for this one? We do not. So we can just do the limit as x approaches 2 of f of x minus f of 2 over x minus 2, which for this one is the limit as x approaches 2 of, let's see, what was it? It was 48 t plus t squared minus t to the third over 12 over x minus, oh wait, over x minus, let's see, we need this part is just f of x. We need f of 2, which f of 2 would be 48 times 2 plus 2 squared minus 2 to the third over 12. So 48 times 2 plus 4 minus 8 over 12. Gosh, this is awful. Is this going to even work? Maybe this was calculator active. Somebody else type that in and see if you get 298 over 2.
What is that? 140?
Oh, I'm sorry. It should be over 3, not over 2. Because you're right. That would reduce.
How is it up with 10?
I just, you got 48 times 2 plus 2 squared, which is 4. 2 to the third is 8 over 12. That's where that fraction is coming from. You're getting 8 over 12, which reduces to 2/3. I think I did this calculator active. I think I had to have. Because, I mean, I've been letting it, everything we've done so far, it doesn't have to be calculator active because you could do it by hand and it's not too terrible. That, I don't think we're going to be able to factor right there. I'm pretty sure we're not going to be able to factor that. So, everybody grab your calculator. All right, and here's what we're going to do. So let me split screen this. All right. So, let me show you this way. This is something good to know how to do on the calculator. All right, I could type in this limit using what I have right here. But it is kind of difficult to do that and get all your parentheses in the right place. So let me show you a shortcut on the calculator. This is actually going to be good for you guys to see on the calculator. Go to y equals and put in that equation 48. We're going to use an x plus x to the second minus x to the third over 12. And make sure it looks right. So type that into y equals. It will make doing this problem much easier. Okay? All right, so we are going to go back to the home screen. So if you hit that home button right below the green button, we need to do a limit. So that's calculus. We're going to do F3 and number 3 is limit. And we need to be doing f of x minus f of 2 over x minus 2. You can use your y1. Let me see. Is this? I know it's hard to see. Let me see if I. Does that help? That makes it worse. Does this help any? No, but the brightness maybe. Maximum brightness. Contrast helped a little. Should be looking up here. A little better, maybe. So And I know, I'll zoom in as far as I can. So, what we're going to type in is we're going to type in, you're just using the letter Y1. It's not a special button. The Y is right next to the X and a 1. So type a Y and a 1 of X. That's, oh wait, before you do that, because this is a fraction, we need parentheses around the top, parentheses around the bottom. So go back over here, put another extra parentheses. Okay, so you should have limit. You should have 2 parentheses, y1 of x. That is like doing f of x. All right? And then we're going to do minus y1 of 2. And close that parentheses for the top. F3. And then go down to the 3rd line. And then, that's just the top of the fraction. We need to do divided by, and then we're going to do parentheses, x minus 2. Close your parentheses. And for the calculator to know what you're approaching, you got to do comma x, comma 2. I'll write this out here in a second because I know it's hard to see. And close your parentheses. So what I typed in, I did limit. It opens a parentheses automatically. I open another one. I did y1 parentheses x minus y1 of 2 divided by x minus 2 comma x comma 2, close your parentheses. What I just wrote here, I wrote on the screen for you guys to see for being able to type it into the calculator. When it comes to free response questions, you can't do that. You can't put calculator notation. You would need to write this limit notation that we had right here. Also, I used x's instead of t's throughout this whole problem. I should have used a t, but now when you type it in the calculator, just use an x. It's easier than using a t. It does have a t. You could use a t if you want. All right, so we're getting 51 for that. So that is our answer.
51 cubic meters per hour.
Cubic meters per hour. Okay, questions? All right. The assignment tonight, it came from AP Classroom, but it's just a worksheet. I just printed it. You got 4 multiple choice, and then there is a free response at the end. It looks long, but it's not really. It just has big graphs.
But I see a staple.
I know.
Staples make things.
It's not as bad as some things. Those multiple choice questions take up a lot.
Bye.
There's not a lot of room on that last free response question, so you might want to be careful with it. You may just want to write it on another sheet or on the back.
This is our homework tonight, right?
Yes, homework for tonight. You also have your free response questions are due on Friday, so don't forget about them. The first one, we're going to learn a shortcut tomorrow. We'll make the first one a lot easier. You may want to hold off on doing that first one. The second one, we will not learn a shortcut for it until much later. So the second one, you're going to have to do with limit definitions. So the second one on the free response, I would go ahead and do it sooner rather than later. All right.